While we are talking about logarithm, I just want to point out a process called logarithmic differentiation that allows us to simplify some calculations when we differentiate complicated expressions. So let's say we look at a function that would be purposely horrendous to differentiate, namely x squared plus 1 cubed multiplied by x ln of x, all this divided by x cubed root of x to the fourth plus 3. Well, if we're going to differentiate that, well, one observation would be that we can cancel an x with the x cube. But other than that, we would have to start with the quotient rule, which would give us something complicated. And then when we differentiate the top, we would have to differentiate on one hand the product of x squared plus 1 cubed with ln of x. And in the first term of the product, we would have to differentiate a composite because x squared plus 1 is raised to the power 3. So all this already would give us a pretty complicated expression just for the derivative of the top that we would have to multiply by bottom unchanged and then subtract derivative of the bottom, where we have again a product, and in that product again a composite. So all this would give us an enormous expression. So it's certainly doable, but one way we can use logarithms for these type of things is by taking advantage of logarithmic laws. Namely, we've seen that natural log converts product into sums, and products are complicated to differentiate, right? The product rule is complicated, but the sum rule is easy. So that indicates that maybe we could use natural log to transform product into sum to get something easier to differentiate. Similarly, quotients are complicated to differentiate, but sums or difference are not. And the log of a quotient is the difference of the logs, and therefore we could transform quotients into things easier to differentiate. Similarly, powers, in particular when we plug something into a power and get a composite, can be complicated to differentiate, but the natural log transforms that into a constant multiple of something, which is easier to differentiate. So trying to take advantage of this, we're going to call this function y and first calculate the natural log of y and use the logarithmic laws to simplify this. Simplify from the viewpoint of differentiation, in other words, we're going to convert product into sums, quotient into differences, powers into constant multiples. Once we've done that, we should have an expression that is easier to differentiate. And so we're going to calculate the derivative of this new expression, natural log of y. On the other hand, because we are differentiating natural log of a function, what we obtain is the derivative of the function divided by the function, so y prime over y. Remember what we are looking for here. We are looking for y prime. So once we've obtained the natural log of the derivative of the natural log of y, we just need to multiply that by y, and we get y prime, which is what we're looking for. So let's take a look at what we get in that particular case. The natural log of y, it's the natural log of our expression here, and we can apply the logarithmic laws to simplify. I could do that in just one step with a little bit of habit. It's pretty easy to do, but here I'm going to do it step by step. So we have a quotient, so a log of a quotient is the difference of the logs. So we get natural log of x squared plus 1 cubed multiplied by x ln of x minus ln of x cubed square root of x to the fourth plus 3. So we have products in each one of the two terms, and we can use the fact that natural log of a product is the sum of the natural logs. So we get the log of x squared plus 1 cubed plus the log of x ln of x minus the log of x cubed minus the log of the square root. Now we can use the fact, well, for the log of x ln of x, we can again use the laws for log of a product. It's ln of x plus log of ln of x. And then we can use that we can pull out exponents. So the exponent 3 in the first term, exponent 3 in the third term, and exponent 1/2 in the last term, because the square root is simply power 1/2. So applying that, we obtain 3 ln of x squared plus 1 plus ln of x plus ln of x minus 3 ln of x minus 1 half of ln of x to the fourth plus 3. So that's ln of y. Of course, some terms can be simplified. Ln of x minus 3 ln of x is just negative 2 ln of x. But in any case, now we have something much easier to differentiate. So if we differentiate that, when we differentiate 3 natural log of x squared plus 1, it's a natural log of a function, so we get derivative of the function divided by the function. So in this case, 2x divided by x squared plus 1. Derivative of ln of x is 1 over x. Derivative of ln of x, again, it's derivative of the function, 1 over x, divided by the function, ln of x. So we get 1 over x ln of x. Minus 3 over x, and then for the derivative of natural log of x to the fourth plus 3, again we get derivative of the function, 4x cubed divided by the function itself, x to the fourth plus 3. So simplifying, we get that the derivative of the natural log of y, which is just y prime over y, is given by this expression 6x over x squared plus 1 minus 2 over x plus 1 over x ln of x minus 2x cubed divided by x to the fourth plus 3. That means that y prime is just y multiplied by this expression. And we just substitute for y its value, and we obtain y prime in function of x. Now we could do a lot of other examples, but I just wanted to illustrate this technique on one particular example. There's only one maybe caveat here in the process. You see that the function f at the top is defined as long as x is positive, and I need x positive to be able to define ln of x, and under that condition everything else is well defined and the function is differentiable. However, sometime in the process I had a natural log of x, and that would be defined only if natural log of x is positive. In other words, if x is greater than 1. So, assuming that we restrict ourselves to the places where everything is well defined, this works just well. There can be a little bit of problems of domains of definition in this process. But with that concludes a study of natural logarithms, so you can turn to homework.